Welcome to yet another mathematics session. Now, last week we concluded on a long and lengthy subject or aspect of mathematics, and that's talking about the shapes in general. We started from the trigonometry, which concluded on three-sided shapes, and then moved on into circles as part of our adventures into plane shapes, and then rounded up with solid or three-dimensional shapes. Of those three-dimensional shapes, we considered the cube, the cuboid, the cylinder, the cone, as well as the pyramids. From all those shapes, we could see that they derive similarities from their counterpart plane shapes, and that the calculation of the surface areas as well as the volumes were all in terms of those plane shapes. For instance, if you are looking for the cube and you are looking for the volume of the cube, you'd be looking at those volumes based on the sides for the respective squares within them. Similarly, if you had the cuboid, you'd be looking at the volumes in terms of the respective squares or rectangles within them, and so on and so forth. This shows exactly how important those concepts are as far as mathematics is concerned, as well as the outlook they portray in the real world. Now, today we'll be looking at yet another important concept of mathematics that also shares that kind of major importance, and that's the concept of set theory. Now, from set theory, we would look at how exactly we can write sets, what exactly sets are, what are the usefulness we can have for sets, how exactly can we operate or interact within two or more set forms, and what kind of questions can we have in sets and set theory. This part of mathematics is very, very important. Why? Because it's easy to have a lot of multiple choice word problems coined out from this kind of questions. You can have a single set theory question attached to 4 or 5 questions underneath it using that same single set theory. That's how important it is. It allows us to extend the concept of mathematics towards majority of the concept forms we have as far as mathematics is concerned. And the moment we take the definitions of what sets are, we would begin to see exactly why this set theory is very, very important. So without wasting time, let's dive into what exactly sets are. So first and foremost, we'll start with the basic definition of sets. Now, for sets or a set, we refer to a set as a collection of well-defined elements, a collection of well-defined elements. Now, why exactly do we have to refer to it as well-defined? We say well-defined because for those elements or members of that set, so when we say elements of the set, we are simply saying members of the set. For those elements within the set, they have to verify or they have to follow a streamlined set of guidelines for them to be members of that particular set. And that's why they have to be well-defined. A good example is, for instance, your mathematical set, which I'm sure almost every single one of us own. In the mathematical set, you have your compass, your protractor, your divider, your set squares, your ruler. These are all members of the mathematical set. They are elements of the mathematical set. And they are well defined. Why? Because every single instrument you have within the mathematical set serves a purpose for which you bought the mathematical set itself. In purchasing a mathematical set, you purchase the tool that could help you plot graphs, draw tables, or draw experimental shapes. This is the reason why you got yourself a mathematical set. And every single instrument you have within that mathematical set serves to follow through with that same responsibility. For instance, when you use your compass, you are simply seeking to draw out curved shapes. When you use your ruler, you are simply seeking to draw out straight lines or straight diagrams. When you use your set squares, you have your angular forms that you seek to find. The same thing happens whenever you use your protractor and every other shape you will have within the mathematical set. So in that collection, they are well defined. But that does not mean we just have inanimate objects as your set forms. No, you can also have set forms for your normal human beings, for instance. Each and every single one of us have at one point in time been a student of a particular school, whether it's a primary school or even a secondary school. As a student in that school, that secondary school or primary school becomes your set. And then you as a student within that school becomes the element of the set or a member of the set. So when we say a set is a collection of well-defined elements, any single umbrella body that houses any kind of element, any kind of member, that umbrella body can be called a set. So a classroom that contains students in that class, for instance, a class of SS3 students, that's a set. And then the students of that SS3 class are the elements of the set. You have a school. All the members of the school are part of that set. You have your parent-teachers association, your PTA, that your moms and your dads are members of for your school. That PTA is also a set form with the members being your parents. You also have cooperatives, a set. You also have various national bodies. Your federal government in itself, your executive arm of government is a set consisting of elements which include your president, your vice president, your governor, your deputy governor, and so on and so forth. You have the legislative arm of government. That's also a set containing members like your speaker, your deputy speaker, your senate president, your deputy senate president, your clerk of house, and so on and so forth. This shows you that the concept of sets is not just limited to just what you have in mathematics. This is a concept that is wide-ranging and encompassing in every single field that exists in real life. So, a set, collection of well-defined elements. Now, for this collection, we can write out the members of the set in two broadly different ways. We call those two ways, first one is the listing form, and then we have the set builder form. Now, how exactly we decide to write the members of the set is dependent on what exactly we wish to extract in the set. For instance, in your legislative arm of government, we can express that set form in terms of each individual member of the Senate, for instance. Let's say the Senate House. Each individual member of the Senate can be listed. So you can have, okay, member of the Senate Western Senatorial District, the Eastern Senatorial District, the Northern Senatorial District, and so on and so forth. And then we list out each member of the Senate. That is what we call a listing form. We can also decide to say, all right, instead of listing out each individual members, we can also congregate them into a kind of collection in itself that will house a particular group of members within that set. So for instance, we can have Nigeria as a set. It's a country and it's a set in itself where all the members of Nigeria are the Nigerians and they are the elements of the set. We could group them into separate clusters. For instance, in Nigeria, we have the Yoruba cluster, we have the Igbo cluster, we have the Hausa cluster, we have the Efik Ibibio cluster, we have the Tiv cluster, and so on and so forth. These are clusters that can be used to represent the entire set. When we formulate or express sets in that form, we can say that we are experiencing the set builder form. Now, we have looked at it in the real life perspective. Let's now put it into writing as far as mathematics is concerned. For the listing form, we can express a set A to be equal to 1, 2, 3, 4, 5. This set A has been written in listing form. How do I know this? Because I can distinctly point to each and every single member of the set. I also can be able to give them placeholders. When I say placeholders, I mean this is the first number, second number, third number, fourth number, fifth number. First position, second position, third position, fourth position, fifth position, and so on and so forth. So listing form is a form of writing sets and their elements such that each individual element is assigned a position and can be written exactly how they are listed, right? For instance, a general set can be the set of natural numbers, and we call the set of natural numbers as the set of counting numbers starting from 1, 2, 3, 4, 5, and it continues infinitely, right? The set of natural numbers written in this form has been written in listing form. Why? Because I have been able to assign positions to each number, first, second, third, fourth, fifth, and I'm saying that every single member of the set of natural numbers will follow that same listing pattern. Now, notice these 3 dots. These 3 dots, or the presence of these 3 dots, is to tell you that there are numerous amount of terms beyond that point, or that I have decided to represent with these 3 dots. We call these 3 dots in mathematics, we call them the ellipses. The ellipses. It's a representation of the fact that there are numerous amount of values beyond the point where we have written or listed. However, we are assured that those set of values follow the pattern to which the earlier values we wrote followed. What does that mean? It means that in this case where the set of natural numbers has been written as 1, 2, 3, 4, 5, I'm saying that for this ellipsis, it contains values that will follow the same pattern. So after 5, I expect to have 6. I expect to have 7. I expect to have 8. I expect to have 9. I expect to have 10, 11, 12, and so on and so forth. So the presence of an ellipsis is telling you 2 things. Number 1, there are numerous other results. 2, those results follow the same pattern as the earlier written results. Those are the 2 most important things you need to know about the ellipses. And so you'll see that the earlier set of values written follow the progression as a normal counting sequence. Their common difference is 1. We have, of course, talked about the concept of arithmetic progression and geometric progressions. So the common difference here is 1, which means that the next term will also increase by that common difference. From 5, I expect to go to 6. From 6, I expect to go to 7, 8, 9, 10, 11, and so on and so forth. That is a very, very important use of the ellipses. You can also use it to represent a set that contains numerous values such that you have a good idea of where the end point is. However, there are so many values that you can't really afford to write all of them out. For instance, in this case, the ellipsis is the last written parameter. Why? Because for the set of natural numbers, we have absolutely no idea where it ends. We know where it starts from, but we have absolutely no idea where it ends. So the ellipsis ending this set shows that there are numerous other values such that we don't even know where those values end. However, if I have a set, out of this set of natural numbers, I want to define a set of numbers from 1 to 100. Or let's say set of natural numbers from 1 to 100. In this case, I have a start point which is 1. I have an end point which is 100. However, for this if I were to decide to list out all the values one after the other, it will take me a long time to reach 100. So in that case, I can simply list out some first few starting parameters, include my ellipses, and then include my last value. What is this telling me? It is telling me that by the presence of the ellipses, there is a lot of values that I have decided not to write, and those values follow the same pattern as the topmost values. And the moment I express those values in detail, I will stop those values the moment they get to 100, which means 100 is my last point. That's the difference between A and the set of natural numbers, because in this case, there is no last point. So even if I get to 1,000, for instance, I have to go to 1,001. Even if I get to 1 million, I have to go to 1,000,001, right? Because it's a continuous process. However, in this case, the moment I get to 99, I get to 100 and I'm done, because 100 is my end point. So the use of the ellipsis is, again, to showcase the fact that there are numerous amounts of terms, and two, that those terms follow the same pattern as the starting pattern. So once you're able to identify that, you can add in your ellipses to any kind of set notation. These notations are all the listing forms. Now, all of this, we can rewrite all of this also in terms of the set builder form, or the set builder notation. In terms of the set builder notation, instead of listing out these parameters or listing out these elements, we decide to symbolically represent the sets by using symbolic notations for all of them. In order to do this, we will have to provide detailed explanations to some of the symbols used, so that we have much more clarity as regards how those symbols work. So, of course, this is a set of natural numbers. Let's take time to also define one more important set that we can write as a listing form, and that is the set of integers. Set of integers. And what are the set of integers? This is the set of positive and negative natural numbers, including 0. That's how you define the set of integers. This is the set of natural numbers. When you take all the natural numbers and then you negate all of them, you get the negative natural numbers. And then if you include 0, you will now have the set of integers. So we can write the set of integers as the ellipses from the negative end, -4, -3, -2, -1, 0, 1, 2, 3, 4, ... in listing form. So all of those sets that we have written in listing form, we will also write them in set builder form. But before we write them in set builder form, let us first and foremost provide explanations into the notations that we will need in order to be able to write out the set builder notations. So let's take those notations one after the other. We'll start from simple and then we'll get right into it. First off, we'll start with the basics. The universal set, which we usually symbolically represent as a curly U. The universal set predominantly means the set of values the set that contains every single element for that particular question. Again, the universal set is the set containing every single element for that particular question, which means for each question you pick, the universal set can change. Your universal set for each question takes all the possible set of members that you can have, which means once you declare your universal set, it is no longer possible for you to pick an element outside that universal set in that same question. That is the most important set that you will have for any question you would have. And that's why we call it the universal set. It is usually denoted by a curly U or in some books as the curly E. Those are two ways in which you can find it. It's very, very important to keep the universal set in mind. Now, from the universal set, we can generate what we call the subsets. The subsets are now the different portions that have been extracted from the universal set. So I give you an example. For instance, in your secondary school, you find out that secondary school is your universal set, because when you go into the secondary school, you are wearing the school uniform, you are wearing the school notes, you are bringing your school notes, you wear your school kits, you go into the classes provided by the school, you spend your entire academic life within that secondary school until you graduate. So within that process, your secondary school is your universal set. Now within that secondary school, each and every single one will have its own assigned class. It might be in SS1, it might be in SS2, you might be in SS3. Those classes are now subsets of the universal set. They are portions that have been extracted from the universal set. It is very, very important to note this. Now, of course, within those subsets, it is also possible to extract another portion from that subset itself. So within a portion, you can extract another portion from that same earlier portion you got. What does that mean? It means as you have the secondary school, you have gotten your SS1. Within SS1, you can have SS1A and say 1A is the science class. 1B is also a science class. 1C is a commercial class. 1D is also commercial. 1E is art class, and so on and so forth. So within SS1, which is already a portion of the secondary school, you are now extracting science, commercial, arts departments as separate portions yet again. This is the concept of what the subsets represent. And we usually denote it as a representation of the subset towards the universal set. So this symbol in the middle is usually called, or is usually read as, is a subset of. So what this means is saying A is a subset of U, which means A is a subset of the universal set. You can also have subset of another subset. For instance, when we talked about A being a subset of B, that is when I said the science class is a subset of SS1, the commercial class is a subset of SS2, and so on and so forth. So you can also have A being a subset of another set itself. These are very, very important concepts as far as subset is concerned. Now, the subset or subset notation splits into two. We have what we refer to as the proper subset, and we have what we refer to as the improper subset. A proper subset is a subset such that the first set is completely contained in the second one, which means the first set is smaller compared to the second set. A good example is where you pick that secondary school as your universal set, and then you pick SS1. The SS1 is usually a proper